It is my pleasure to invite our today's speaker. Michael Batty is, I'm going to get this slide up too. Sorry, this is something wrong here. Bear me with 1 second. Yeah. Michael Batty is a Bartlett Professor of Urban Planning at the University College London, where he also chairs the Center for Advanced Spatial Analysis, or CASA. Professor Batty's research group is working on simulating and visualizing long-term structural change in the dynamics of cities. He has worked on computer models of cities and their visualization since the 1970s and has published several books, including Cities and Complexity with MIT Press in 2005, which won the Alonso Prize of the Regional Science Association in 2011, and most recently, The New Science of Cities, also with MIT Press, published in 2013. His blog, www.complexitycity.info, covers the scientific underpinnings of city science and technology and includes his frequent posts and lectures on big data and smart cities. Prior to his current position at UCL, Professor Batty served as a professor of city planning and dean at the University of Wales in Cardiff, and then director of the National Center for Geographic Information and Analysis at the State University of New York at Buffalo. Professor Batty holds a bachelor with honors in town and country planning from the University of Manchester and a PhD from the University of Wales, Institute of Science and Technology, where his dissertation focused on pseudodynamic urban models. He is a fellow of the British Academy, the Academy of Social Sciences, and the Royal Society, and he has been awarded the Queen's Birthday Honours in 2004 and 2013. In 2013, Professor Batty received the Lauréat Prix International de Géographie Vatrin-Lud, generally known as the Nobel Prize for Geography. In 2015, he received the Founders Medal of the Royal Geographical Society, for which his work on the science of cities, and in 2016, he received the Gold Medal of the Royal Town Planning Institute and the Senior Scholars Award of the Complex Systems Society. He has been awarded honorary doctorates from the State University of New York and the University of Leicester. Please join me in welcoming Professor Mike Batty. And I will stop sharing, so Mike, you can go ahead and share your screen.
Okay, thanks very much, Andres. So let me share my screen. Okay, there we go. And let me just move a little bit of the clutter out of the way. Okay. Okay, well, thank you very much for inviting me, ladies and gentlemen. It's a very interesting series of talks that you have here. Today I'm going to talk about really the design process. I'm not going to talk particularly about urban design and the applications in that sense, but I'm going to talk about the process of generating urban designs, etc., based on the idea of pooling opinions to some extent, the idea that the design is collective in that sense. If you want to actually follow the PowerPoint, or in fact look at the PDF of the PowerPoint, basically, then you can get it from my website, which is the long version there, but also the tiny URL, which is MTU7BXYJ. I'm pretty sure you can't remember all of that, basically, but I'll say it again at the end. So you can get a copy of the PDF by clicking on one of those links, basically. Okay, so what I'm going to do is I'm going to talk about a model of design to some extent, where design is participation amongst interested actors or agents. And what I will do in this talk is, first of all, I'll illustrate a very simple model of group dynamics in which agents begin to pool their opinions and move towards some kind of consensus. The second aspect of this is the actual problem to which this is applied. And I'll begin with a very simple problem and take it a little bit further in terms of a land use allocation problem. And then lastly, talk about a problem of urban design in the heart of a big city, which is in fact in London. And the third element of this is the process of coming to some sort of consensus or not. Essentially, if the group is connected in some way, then it'll move towards a consensus in this sense. If it's disconnected in certain ways, and it depends on the complexity of this of these relationships, then it will not reach a consensus in that sense. So let's actually begin with the example itself. So let's take a very simple set of actors, 4 actors or 4 agents, 1, 2, 3, and 4. We've labeled them, and those are the interactions between them. So you can see that they're connected both directly and indirectly in this particular context, in this particular way. And what we're going to do is to represent the relationships between them as a graph. So on the right-hand side, we've got the 4 actors, basically, and all potential links between them as we've mapped them out in terms of the first element. So you can see that actor 2 is to some extent on the edge of the group in this particular context. Actor 3 is probably the most centrally related, largely because there are interactions with the other 3 actors, basically 1, 2, and 4 in this context. That's not the case with the other actors. So there is structure to this in some sense, and the process is really very simple. It simply begins by giving an opinion, if you like, to each of the actors. And the actors swap their opinions rationally, and they make a rational choice between the opinions they receive, basically, in their own opinion in this sense. So it's an averaging problem in that sense. It's a very well-known problem, as we'll see in a moment, but it's an averaging problem in this particular context. So let's actually see how it works on a very simple problem. The problem, in fact, is a numerical problem where we give each of the 4 actors a value in that sense. So for example, let's actually identify the number 10 with actor 1, 90 with actor 2, 30 with actor 3, and 60 with actor 4. And you can see that there is substantial difference between their particular opinions or their values in this particular context. And the process is one of averaging, in a sense. Now, in a way, if you've seen this sort of thing before and reflected on it in that sense, it's pretty obvious what's going to happen is that eventually all of these opinions or numbers will be communicated to all of the actors in turn, and the weights which are implied by who they're related to, the links in this sense, or the interactions, will determine the ultimate average. Of course, if we looked at the values of this, 10 to 90, so 10, 90, 30, and 60, if we took a simple average, the simple average of this would be 47.5. And what I will illustrate by swapping these things, that we don't come to a particularly simple average, but we will come to an average which is between 10, 90, 30, and 60 in that sense. So in other words, the process is to swap, as it were, these opinions according to the network and to make a rational compromise in that sense. So let's take actor 3, who is in some sense the most central in this little network. And actor 3, for example, first of all, links to actor 1 in this particular context. So in terms of the process of communication, actor 1 transmits the value 10 to actor 3 in that sense. So actor 3 has got his or her own value of 30, and then gets actor 1's 10, basically. Actor 2 is 90, transmitted in this way. Actor 4 is 60, and in that sense, and therefore actor 3 has received all of the information in this context and produces a compromise, which is 47.5. Now, 47.5, in fact, is the simple average of all of them in that sense. And the reason why it's 47.5 on this first iteration is because actor 3 is connected to all of the actors, including him or herself in this particular context. So you can see on the first pass, if we do this for one iteration, then you can see that we're beginning to average the values in this particular context. And if we then actually go through this process continually, or iteratively, I should say, let me just go back to the graph, basically. If we take those values the 233s, the 60, the 47, and we pool them again in this particular context, then we'll reduce the differences between them. But the differences will be reduced not as a simple average, but on the basis of transmission. Now, of course, it's a very simple problem in some senses, that I guess the power of these things probably comes from scaling it up to a real problem in some sense, or a much bigger problem in this particular way. And we'll see how that works in a moment. But this is the table. This is the table of that you get if you iterate out. So if we go through 10 iterations of this process, then you can see, to all intents and purposes, by the 10th iteration, we've actually produced an average in this sense. Okay, so in fact, if we have a network where everything is connected to everything else, we get an immediate consensus. We get a simple average in this particular way. If we have a network like this, for example, where 1 and 4 are connected and 2 and 3 are connected, we don't get a solution at all. We get two solutions. We get the simple average between 1 and 4 and the average between 2 and 3 in that sense. So you can begin to see that we can think about this as a process of getting a consensus or not getting a consensus, dependent upon the structure of the method in that sense. Now, in this particular context, in this particular version of the pattern of interaction, basically, then if you look at actor 2, then you can see that actor 2 is connected to actor 1 and actor 3, and transmits from him or herself to 1 and to 3, and of course the little self loops really maintain that the opinion they have initially is part of this process. But in the case of actor 2, in this sense, transmitting to 1 and 3, they will continue to transmit to 1 and 3. So even though 1, 3, and 4 might be averaging and getting rid of their differences, actor 2 will continue to transmit in this sense, and eventually what will happen is that the dominant opinion in this particular structure will indeed be actor 2 in that sense. Okay, so we can array these things in terms of, there's our 4 actors again, and those are the relationships between them, acted from time t to time t plus 1, or iteration t to t plus 1 to t plus 2, and so on, until we get the average. Now, if we turn that network around in some sense, so what I'm actually doing here is to actually turn it around, to rotate it really in this sense, then we can see that this is beginning to look like something that's very familiar in the context of machine learning. And there are indeed a number of issues that really spin off from this in terms of this idea about neural nets and so on. Okay, you can see that what we have there is simply the process of averaging, as shown in this different light in that sense. So to some extent, what we're not doing in this thing is we're actually not going through a process of iteration by bombarding the problem with new information each time. Were we to do that, then we'd be very much in the business of getting the network to learn about the problem in this particular context. And I'll say something about that a little bit later. Okay, so the summary so far, we have the network, the averaging process, if you like, the machine, basically. So there's, again, another little graph, different from the previous one in that sense. Those are that's the adjacency matrix of that particular graph, and the weights in some sense in this way. There's our kind of iterative process in some respects, and that's the process in this particular case, as taken from a different example, of averaging the five actors or the 5 factors in this particular context, and you can see the convergence in this way. Now, again, it'll come as no surprise to you that there is quite a lot of formal structure to this process. You can think of it as being a linear process of this kind, and indeed it turns out that this is a Markov process. In some respects, the Wij in this particular formula are the weights, basically, or the pattern of interaction, and the Aj represent the different initial opinions, if you like, or factors, or whatever we like, and that's the process of averaging. Of course, if we go through that process where we take A t plus 1, which is the output from the linear weighting, basically, in a sense, and we feed it back and we iterate in that sense, then we do ultimately produce an equilibrium equation, which is the Markov equation, basically, in this particular context. We can modify the model in the following sense, although we won't do, I'll just illustrate it, that we can add a difference in the opinion, we can add external information each time in that sense, and then you again see a particular familiar structure which has been widely investigated in many different fields. Okay, so let's look at an example. Let's look at an example in terms of this spatial averaging, etc. So we're going to choose a set of factors showing the desirability of land development. You might think of these as the opinions over which land is developed, and we'll express these as maps, basically. The maps conflict with one another, so the maps are associated, if you like, with the actors. Each actor has a map, if you like, of where the best location would be for, let's say, a housing estate or something of that sort. The maps will conflict with one another in this particular context, and indeed we can form a network showing the strongest conflicts between the various maps, which are the actors' opinions in that sense, showing measures of similarity or dissimilarity in this particular context. And if we make sure that the network is connected, which of course it will be, because we'll be comparing every opinion with every other opinion, then this implies a set of weights, and we can actually perform the averaging in this way. So let's take 12 different factors. These, if you like, are 12 different opinions about where a particular facility should be located. In fact, it is a real town. It's the town of Macclesfield in south of Manchester in this particular context. And I think, in fact, the next slide will give you an idea of the scale of this. Basically, it's quite small scale, about 6 miles across and about 10 miles north-south, basically, in that sense. But the important thing to note is that the actors, or the 12 actors who have identified, we've identified the factors or the opinions in this sense as maps, basically. The 12 actors, or the 12 factors, we might think, we've translated it from actors to factors in this sense, really represent issues pertaining to the physical desirability of land in that sense. So you can see factor 1 is accessibility to existing urban services. Factor 2 is cost of spatial congestion, and so on, in a sense, which is a fairly typical list that you would see in many kinds of overlay analysis in that sense. Okay, now the relationships between them I show in this particular diagram here. Those are the relationships, so it's not a completely connected structure. We've given it some structure at that point. The map of the town is in the top left-hand corner, so it's about 6 miles across and about 10 miles north-south, as you can see, the town of Macclesfield. And we've represented the land desirability surfaces as a contour maps in that particular context, rather than sort of binary maps, which we showed previously. Now, if we go through the process that I've been talking about, then we average basically the factors in this particular way, and ultimately, because the graph is connected directly or indirectly, so it's strongly connected in terms of graph theory, then ultimately we will get some sort of consensus, which is reflected on the weights that are implied in terms of the graph. And if we turn it round, then we can begin to think of this as a kind of a neural net. It's very different as the process from a neural net, which really is taking a set of factors on the left-hand side and bombarding the net with different factors, basically, from different examples, etc., which might actually then train the net to actually produce things. In this particular context, we're not training the net in any sense. We've assumed the net, basically, and this is the iterative process. But the issues are the same sort. We could, for example, extend the problem into a different domain, where, for example, we could take different factors, etc., and continue to put them into the net. I'll come back to that in a moment. Okay, so this is the picture that we actually get if we go through the process that we show in this particular context. And you can see that ultimately, after about 10 iterations or so, the differences are ironed out and we produce a picture, basically. So you could think of that as being 12 different sets of opinions represented as maps. We can associate them with individuals or actors, but we might think of them as simply being differences in terms of the problem. The relationships between them then need to be determined to get the network, and ultimately the process of compromising or averaging produces the final map. So in other words, you can think of the final map as being the solution to the problem. This is, for example, the best locations for the location of this particular facility in that sense. Now, it's not very different from a good deal of map overlay analysis, except that we have a process of determining the weights, basically, in some sense, which really relate to the interactions between the factors in that sense. We might think of this as even being a correlation matrix between each of these 12 factors and working it in that particular way. And that really maps it onto all sorts of linear statistical models that are similar to this way. Okay, now, one of the things that we've not done, basically, and but we're thinking about, I'm thinking about a little bit in this particular context, is to think of this as being a neural net where we take a series of factors pertaining to a particular town, for example, and we take a series of towns, many towns, if you like, with factors which are arrayed in this sense, the same sorts of factors, and we actually bombard the net in this particular way with these factors. Let me just do that again, basically, to give you an idea. Now, we've not done any of this, but basically, if were we to do this, then we would actually begin to train our net in this particular way and begin to alter the weights as we go through. And that's a different problem from the one that I've really related in that sense. Okay, let me move a bit of stuff. My screen has got a little bit of the clutch on it instead. Okay, so let me actually look at a slightly more elaborate construction in terms of constructing our network. Each map could be coded in terms of a binary code as some level of desirability or undesirability, etc., with a 0, 1. So we can think of the maps as being represented in this way, and if we represent the map as a vector, whoops, yeah, in this particular context, think of the map as a vector, basically. Then what we might think of is that the maps can be represented. Sorry about this. Okay, let me just go back. Yes, the maps can be represented as vectors in this way. So, in other words, this is a map, if you like. Each agent has a map, or each factor is an agent who has a map in this particular context. And then we have a map of location. So we have a non-square matrix of a binary matrix representing the differences between the maps which each of the actors hold in that sense. So that's our matrix M, basically. Now, I should say that if you look at this carefully, then you'll see that I've dropped one cell in the map because my last example relates to 8 locations rather than 9. So we've got 8 locations here. Basically, on the previous slide, we had 9 locations, but that's irrelevant. The map, in fact, is the example I'll show you in a moment is 8 locations. So in other words, we could look, having got this matrix here, we could look, for example, at the relationships between the actors in terms of how their locations were different in that sense, or we could look at the relationships between the locations in terms of how different the actors here. So we have this non-square matrix M. If we were to actually look at the relationship between actors and actors through locations, we would be powering the matrix in one way. If we looked at the relationship between locations and locations via actors, then we would look at it another way. And in this sense, we can begin to think about extending our problem into one where we can think of a primal and a dual. So, for example, the interactions between agents can be seen in terms of the maps. In the time-honored way, using the convention of forming the similarity or covariance in that sense. So we take the matrix M and we take its transpose, and that produces the relationships between the 6 locations in this particular context, in a sense. And we can do exactly the same, or we can do it in the same way by taking the M matrix and producing a set of relationships between the locations in that sense, 2, 4, 6, 8 in that sense. Yeah. Okay. So in other words, we can think of this as being the primal problem, and this as being the dual problem in this particular context. And so in other words, the S matrix here is the weighting matrix there in the primal problem. Then the A matrix is the weighting matrix in this particular sense. Now, at this particular point, I could stop, but what I would like to do is show you an example of how we can take this a little bit further. In many senses, that I've written about this in the New Science of Cities book that Andre referred to. Then the last section of that book deals with what I've been really talking about. In fact, that's the bit of the book that I don't think anybody ever reads, basically, in that sense. But I've worked on it slowly over a number of years, basically. There's a paper years ago in architectural design where we first did this, and a couple in environment and planning B. In fact, there is a strong lineage in all of this sort of linear iterative thinking that pertains to the way we look at that problem in lots of things. There's a paper by Blondell et al. Called Convergence in Multi-Agent Coordination, Consensus and Flocking, basically. And I believe, I'm not absolutely sure, but I believe that a couple of those authors may be at MIT. I think Professor Sikilis is possibly at MIT in OR, but in fact there's quite a big literature that really pertains to this sort of thinking, which in fact really relates to whole questions about coordination and consensus in linear systems in that sense. Now, I could finish here and not outstay my welcome, but let me introduce one last example to show you where this is going. This is a problem of development in the City of London in the financial quarter, where there's intense pressure to develop and intense control over the environment. In fact, it's so controlled that in this area, there are cameras everywhere. There's a cordon around the city. The cordon basically really relates to issues pertaining to security and so on, cordon around the city. And my example involves a small area near St. Paul's Cathedral, where we've identified 6 key actors and 8 sites. So going back to my example of actors and sites, basically, in a sense, what we've done is to identify 8 big sites and 8 key actors, etc., just as an illustration of how we can think about this particular design problem. Okay, so this is the area of the City of London, basically, and what we're looking at is that area here. There's a lot going on in this area here. It's very historic. The Roman wall basically runs through this area, basically, through the polygon that I've shown there, basically, and that's the Google map, basically. I'll tell you what the different bits are: the actors and the buildings, basically, etc., or the plots in that sense. So that's our area in this particular context. This, in fact, is the site. Which is shown here, basically, is basically a big legal office, basically, etc. The site 8 is, which I've just shown you, is there's the hospital area here, basically, so that's part of the hospital. That's also part of the hospital. Site 6, in fact, is the old General Post Office extension from 1902, which was acquired by Merrill Lynch in 2000, and then when they went bust, it's now Bank of America, etc. This is a residential block, basically. This is a Georgian church. In that sense, this is Namora, what used to be Namora Bank, the General Post Office in 1880, which was then purchased by Namora Bank and is let out. That's Postman's Park, basically. So that's our area. Let me just tell you what they are in that sense. This is what it looks like, basically. Just skipping around. So it's kind of interesting sort of area, kind of Pocket Park and so on. Let me go again, and let me tell you what the sites and buildings are. It's not important to know what the buildings are in this particular context, basically, but this gives you an idea of the variety, etc. Now, the actors and stakeholders, of course, this is all made up to some extent. It's a semi-fictional problem, I suppose, in a sense. The sites, buildings, and locations are real places, basically, and we've just seen those. The actors and stakeholders are the kind of key owners and institutional agents, basically, who are involved in this. There's clearly the city corporation, that's the City of London, basically. The local authority is centrally involved in many of these things. There's residents in the area, etc. There's the National Health Service hospital, St. Bartholomew's Hospital is there. There are developers continuing to look at this area. There are property speculators too, and there are banks, basically, in this particular context. Let me just go back to the picture again and say that the areas basically are under intense pressure. I'm just going to go back to these sites, basically. Since actually I originally looked at this problem, the site called 8 has been redeveloped. It's an office building now. It no longer belongs to the hospital. The bit of St. Bartholomew's Hospital 7 has been redeveloped over the last 10 years, basically, as part of the NHS development. 6 basically has changed its well, it was originally Bank of America, Merrill Lynch, now Bank of America. Originally, in fact, it was the General Post Office extension. 1 is the Aldersgate complex and so on. And 4, 5, 2, and 3 represent the Postman's Park area, the Pocket Park, with 2, the Georgian Church, and 4, the residential bit. Okay, let's go forward to thinking about this. So in other words, what I can actually begin now to do is to think about the relationship between the agents, basically, and the sites and the buildings. So, for example, what we've indicated in this particular context is the interest that a particular agent would have in any of those buildings. So I'm not going to go through them in any detail, but this gives you an indication that there are interests of this sort in the sense. And you can begin to see that what we can do in this interest, this is building up our M matrix, basically, where we can begin to look at the relationships between agents and sites and buildings. First of all, through the relationships between agents and other agents through sites and buildings, what interests they have, and that would give us a set of correlations, a set of weights, essentially. And we can do the same, which is in terms of the dual problem between sites and buildings, and the same themselves through agents in this particular way. So in doing that, this is the M matrix in a sense that we've produced, and these are the relationships, basically, the relationship graphs, basically. We've drawn these as graphs, basically, for the primal problem and the dual problem in this context, and that's another way of representing them in a sense. So here we've taken the relationships, basically, and we've worked it through to produce we worked it through using that linear method that I showed you at the beginning, basically, to produce a kind of equilibrium in that sense. This, if you like, are the importance of the sites, basically, the relative importance of the sites. Once we have the averaging which takes place between the different agents in this particular context. And we can do the same in terms of the differences are marked out in this particular way. Let me just give you the results rather than sort of talk it through in any detail. This is the relative importance of the buildings relative to the agents in this sense, or the stakeholders in this particular context. And those are the relative importance of the stakeholders, basically, or the agents in this particular context. And those numbers are actually produced by the relationships that we showed in terms of the M matrix to begin with, and the primal and dual problems which spin off from them. Okay, now I'm going to stop at that point. I don't know how we're doing for time, basically, but I hope we've got a little bit of time for questions, and thanks for listening. Okay, I'm going to stop sharing my screen. If we need to go back, then I can do. Okay, there we go.
Great. Thank you, Mike, for your presentation. We talked a little bit before this, before you started the presentation, about a certain tradition of planning and landscape architecture called geodesign that is also very much focused on consensus building, or at least a democratic process to design. And you mentioned some overlaps with your thought process on looking at these multi-actor networks and consensus building exercises with relationship to the work of Carl Steinitz or Esri and what Jack Dangermond at Esri has also been, I think, quite interested in. Can you comment on this a little bit, on how this fits into the kind of participatory planning processes using GIS that folks have been talking about?
Yeah, okay. Well, obviously, from what I've said this afternoon, or lunchtime, isn't it, there in America, what I've been saying, of course, is largely hypothetical. The relationships between the agents and the sites, basically, in this particular context, in terms of the last problem, the relationship between the stakeholders and the building blocks, in that sense, or the sites. All of these things are made up to some extent simply to illustrate the idea. Of course, in geodesign is a process where, as many of you probably know, essentially, it's a participatory process in which different teams of people, who you might think of stakeholders or agents, are involved in actually reaching some sort of solution in the context of the problem. So in many senses, what we've thought about, what Carl and me have talked a little bit about, is whether or not we could actually measure the process of interactions that take place in the geodesign problem. In most of his examples of geodesign, he's talking about between 4 or 5 and maybe 10 teams, basically, composed of 3 or 4 individuals who all set out to produce a solution to a particular problem that is posed in that sense. And during the process of geodesign, they begin to swap information. Harishi Balal, who has worked with Carl on developing the software for this, basically enables the different teams to see what every other team is doing in some sense. So the process of pooling opinions in that sense, or pooling ideas, is quite similar in some sense to the implications of what I was talking about in terms of those hypothetical models, etc. So the idea might be, and we've not done anything about this because there's a whole range of other issues that really pertain to how feasible it would be at this point in time, is to think about modeling the process, basically, using these sorts of models, basically. So this is really a speculation that we could actually take the sort of process, take the interactions and the opinions and so on, and the changing solutions to the problem that come out of the process of geodesign from these different teams, and we could try and model it using the kind of thing I talked about, in the talk a moment ago, in that sense. So that would be we've not done this for the simple reason that the geodesign process is not quite set up to do the same sorts of iterative problem solving that pertain to the model in this particular context. And the model is not quite geared in that sense to the geodesign process, but it's close in some senses.
Yeah,
and that would be a way forward in that sense, in terms of thinking about taking a real problem, whether or not the geodesign is a real problem or not is irrelevant, I suppose, but taking a problem where you had interactions of that kind and actually modeling it in that sense and seeing whether or not one would come to the same sorts of same types of solution.
Yeah. If I may, just a very quick follow-up on this. A question that I would have is, where does urban culture come into this representation? And what I mean by that is that when we look at the kind of these interactions between individual agents with influence and power and communication links between other agents, then in some cities, we clearly have a sort of a certain clout of culture that flies over all of these agents, and in other cities, less so. So as a concrete example, like two major cities across the channel, Paris and London. Paris is extremely careful in terms of allowing anything experimental in its built environment. And has therefore sort of historically resulted in a very uniform urban form with multi-actor decisions kind of converging towards a certain kind of outcome that fits in, so to speak. London, on the other hand, has been far more experimental and has resulted in an urban form that is indeed, I think your example from the city is a good one. It's a little bit of a hodgepodge of experiments of different building types, land uses, etc. And I think if you were to put this into this actor network, the question is, where does this kind of influence of urban culture and the norms that dominate over all the actors enter the representation?
It's a very profound question, I think, Andres, in many senses, that in a way, I suppose the cop-out would be to say that the way we define the stakeholders, the number of stakeholders, etc., the way even we define the buildings in this particular context would imply some of those issues that really pertain to these broader questions of culture. In some sense, the stakeholders we have in the City of London at this particular part of the city are really quite conservative in many ways. That there really isn't much. There really isn't much physical change, basically, from what has been built up. I suppose over a period of the last 100 years or so on, there have been more substantial change. There are also a lot of the agencies that are involved in developing in this particular site. So, for example, the National Health Service, St. Bartholomew's Hospital is a hospital that goes back to the Middle Ages, basically, and is a cancer hospital, basically. That's been redeveloped, and quite a sensitive redevelopment in this particular context. So the environment has improved recently. The city are rather conservative, that in this particular context. If you were to move to other parts of the city, behind me, if you can see the bits behind me, sort of, this is the interactive bit of the talk, basically. That's the old stock exchange behind me. Those things look like a Greek temple. It's not been a stock exchange for about 80 years. To my right, or your left probably, is the Bank of England, basically. But behind us, behind me, let me just tip my screen up, in that way. You can see that wall of skyscrapers. That's 22 Bishopsgate, and behind that there's the Gherkin, basically, and there's been a recent proposal to build next door to the Gherkin another Foster thing that's been rejected, which is called the Tulip, basically. That's all that wall of skyscrapers has really been built since the Great Recession, most of them. I don't know whose money it is who's actually built it, basically, but that's very unusual for the city. It's quite experimental in some senses, largely because the city has a low building policy in that sense. So how do we build that in? What I'm saying, back to the talk, I think we build it in by selecting the right sorts of stakeholders that pertain to this particular problem. It's in that context. And what I suppose I'm saying is that different bits of the city have different viewpoints in this sense. So you've got really different cultures representing different bits of the city. So the same corporation, okay, and probably the same politicians and even and planners and engineers and so on, would change their view dependent upon what bit of the city they were in that sense. And that's really saying that experimental architecture, experimental things take place at different points of the city, and other bits of the city are not experimental at all. They're really quite contained in that sense.
Thanks. I'll hand it over to Ari, who has some questions, I think, that have come in through the chat in the meantime.
Yeah, wonderful. Thank you, Professor Batty, for this fantastic talk. So maybe I'll start with a question from the audience on the use of the term city science or urban science. As you know, many of us use it today, but they have different meanings for different people. And so we're wondering whether you can comment a little bit about whether you see a potential of confusion for using it, given that it means different things to different people, and whether you can comment on whether you think there's a better term or whether it matters at all.
That's a good question. Actually, I've talked about that quite a lot recently, sort of, among colleagues in an informal way, urban science. I mean, I call my book A New Science of Cities, meaning not that there is a single science. There are many sciences of the city in that sense. And I think that's the first point, that there is no one urban science or city science. I'll come on in a moment to say something about cities versus urban, basically. But there really is no science. And in some sense, the terminology from the perspective that I'm using it really is really based, I think, on developments that have probably come out of a complexity theory to some extent. Things like scaling, for example, questions of city size, scale, all of this sort of stuff is really part and parcel of this urban science. So, for example, Louis Betancourt's book, Introduction to Urban Science, which is also MIT Press, for example, is very representative of this. Mark Bartholomew wrote a book on cities and dynamics about 5 years ago, basically, which is similar. And it all really comes out of a certain statistical physics type approach. Now, you may say, well, how does that relate to the sort of statistical physics and social physics that people developed in terms of the first urban models back in the 60s and 70s and so on, 50s, 60s and 70s? Well, to some extent, there really isn't a strong link between them, in some sense, that this new urban science, so-called, is really about new ideas that have remained dormant for many years. Questions of agglomeration, scaling, city size distributions, and so on, really pertain to that. I have a very Catholic view, a very pluralistic view about this, in some sense. I think that the term is basically appropriate to these new things that are being thought about, but at the same time, the notion that there is a uniform, homogeneous urban science that sort of extends everywhere, or city science basically, is a non-starter in my view. So I'm a pragmatist in terms of thinking about the terminology. Let me leave it at that. If you want to come back on that, then please do.
No, thank you. Thank you for the answer. So maybe we can switch briefly to a question about the application of the model that you introduced. And in particular, Ryan was asking, how does it connect maybe with the idea of the transect? Ryan, do you want to unmute yourself and ask your question?
Yeah, sure. Thank you for your presentation, Professor Batty. I was just wondering if you're familiar with the transect as a normative tool for planning or even descriptions of geography, and whether the agent-based modeling is something that can be reconciled with the planner's transect.
transact. Can you explain that to me? Obviously.
Sure. So the transect is something that is used in the field of ecology, usually in collecting samples on some sort of
Yes.
line, right?
Yes, yes.
In the planner's domain, there's it's usually modeled as like 6 distinctive zones as a gradient from the most natural preserved open spaces to the most highest density, highest intensity city centers.
Okay, and your question was how does the model that I'm talking about relate to that?
Right, yeah. So lots of planners will use the transect in developing plans for development in different jurisdictions. But I'm wondering if that is something that kind of conflicts with agent-based modeling.
Okay, well, to some extent, I'm not sure necessarily there is an intrinsic conflict in this particular context. That, in other words, that if one is looking at a location problem, then it seems to me there are several different approaches one can actually take, and that an agent-based modeling approach, to some extent, the agent-based modeling approach still has to be adapted to what are the agents in some sense, and how do they pertain to the location problem, etc. That in and of itself is quite an important issue. Whether or not that conflicts with other approaches, such as the transect approach in this particular context, is something that I think is very difficult to say in advance of looking at a direct comparison between a particular agent-based model with presumably trying to solve the same sort of problem as the transect approach in this particular context, the gradient approach in that context. So I'm not sure I can actually give you a definitive sort of view or answer with respect to this particular issue. It seems to me that you've identified the transect approach to one in which one's looking at different locational issues. There are lots of different models that might pertain to the same sort of thing. And again, I go back to this notion of pluralism in modeling, that it seems to me that in our world, there are many models that you can have of the same phenomenon, which are different in some sense, this idea that there are multiple models in that sense.
It may be that I think the crux of the question is how does the kind of actor power network fit with an urban economic model of land values and land densities that emerge, or construction densities that emerge as a result of land values, which is perhaps more of a question of how does bid rent theory work and how do agents bid, or how do their goals change by location, etc. That's an interesting kind of maybe line of considerations. But I do want to point it to Ariana. I think we have at least one more question you wanted to get to. So in the sake of time.
Yeah, absolutely. So let me ask one question and then head it over to Joe, who has another question. So Professor Batty, I'm digging deeper into the model. So you mentioned that to achieve like a single consensus, you need a connected network, right? And in the land use example that you showed, you have complete information because you have a value for each of the pixels in an image. And so I was wondering if you can comment on like whether this is always the case, and if you can elaborate on how you would draw that fully connected network in a scenario with incomplete information.
Okay, well, to some extent, I suppose the real power of this sort of thinking is to think about situations where we don't get consensus, in a way, at a rather nihilistic sort of point of view to some extent, in the sense that if the network were not connected, if you couldn't reach any actor from any other actor, basically, in that sense, then you would not get a consensus. And it may well be that most of the problems that we might set up in this particular context would not necessarily reach a consensus in that particular way. In terms of the way of constructing the network, and I suppose what I was doing was I started off with the assumption of what the network was, and then gradually moved to a situation where you compared with the, let's say, the maps or the opinions or whatever we want to call it, the attitudes, the maps basically with the stakeholders in this particular context, where you looked in this particular way, then there would be situations where, and in fact, in the example in the City of London, I think the residents were only interested in the residential blocks. We didn't specify any interest that they had in any of the other blocks, basically. It so happened that the network that we actually got was completely connected, or was connected in this particular context. But there could be situations where this was not the case, basically. So in some senses, the disconnected network, or the partially connected, I don't want to say disconnected, because that really divides the thing into, two or more problems, two or more networks in a sense, but a problem where we have the inability to transmit from one actor to another, basically, in various parts of the network. And if we can think of very big networks, and by very big networks, I'm talking about bigger than the what I'm talking about here, but we might be talking about 50, 60, 70 stakeholders and so on. Were we to do this for real, basically, this is what I'm saying, then we might get the sort of situation, we may get the situation that you're actually indicated, that there would be disconnection in that sense. So that's an important aspect. I mean, I suppose in a sense to justify what I've been talking about, we're talking really about a way of thinking in some sense. To elaborate it further, one needs to look at lots of different problems in this particular light, and to begin to sort of generalize one's experience from that kind of thinking, really. And in that context, we can begin to see these differences that are really being pointed out, differences from a real situation.
Thank you. Maybe in the last minute, we had a question from Joe. Joe, do you want to unmute yourself?
Okay.
Thank you.
Hi, Mike. Thanks for this stimulating set of ideas. I'll try and be brief. I wrote some notes in the chat. It seemed, because the model is sort of assuming which locations are good and bad from each actor's point of view, that it sort of assumes that each actor knows what they think and are clear about the possibilities, in which case this might be a nice way to deduce after the fact who had the strength of interest and commonality of interest to sort of drive the result. But for most of these situations, actors try to convince other people of their thinking about the pluses and minuses of various choices. The modeling doesn't allow for that. People have to, you'll find the consensus based on people being pretty firm about how they feel. So in reality, as far as driving a decision, then you have both the gaming possibilities, like if the residents are only, they're only interested in one location, in which case with this scheme, they aren't going to have a lot of influence over what else happens. So I guess it seems to be more useful to understand the relative strength of actors in determining a decision that's already made, rather than helping to shape a process where there was an opportunity for people to exchange beliefs about which locations would be good and why.
So to sort of reverse engineer it in some sense, to actually work back to imply, to look at situations where you could identify a number of actors and you could identify a decision or solution or whatever you want to call it that had been made, and to work back to figure out how that might have been made in a sense. Yeah, I think that that's an important issue, notwithstanding the problems of doing that. I think related to that is the notion that, and I didn't really say anything at all about this, is that the process of transmission between the actors can be changed quite dramatically. So, for example, you might find that in certain iterations, some actors don't compromise, etc. So there might be some variation in that sense. There might be a situation where the network changes to some extent. I mean, that was the implication in terms of thinking about the neural net sort of weights and so on. The network might change over time. So after the first iteration, other factors pertaining to who had influenced who basically came onto the scene. So the network actually changes its structure in this context. So every bit of the problem could change in this particular context. And I think that the difficulty in beginning to apply these things, I'm not saying we shouldn't do it, but is it to apply them to real situations, is the fact that the variation in possibilities is so enormous with respect to how an actor might pertain to other actors, basically, and the way they might actually do that, that it really becomes very difficult to actually tune it to a real situation in this sense. But real situations, I think, are things that we need to do to begin to make any improvement, if you like, on what I've been talking about in that sense. I'm not suggesting either, I think, here that that necessarily this is something that one might emulate for a real design problem, etc. I'm saying that in some senses, this is a way of thinking about the problem, basically, in that sense. And it doesn't necessarily discount all the other things that one might do in terms of coming to a solution with respect to some kind of urban design or urban location.
Joe, this reminds me of a recent account I saw from a highway engineer who had operated in New York in the 90s, from the 1950s onwards, and he was writing about how highway placement was a veritable science in terms of slope and topography and optimization for connectivity with adjacent roadways, etc., until a point where he came to realize that highways are actually placed where Robert Moses wants them, rather than any other consideration. So the after the fact power analysis could indeed be very useful, revealing what really happened. But on that note, we are out of time, unfortunately. Mike, thank you so much for your presentation. Really appreciate it. And I would like to mention for everyone else who's still on the line that we have only one more of these talks left. Next Monday, we will be joined by Yves Blau from the Harvard Graduate School of Design. And that will finish off our semester this time. Mike, if you have a couple of minutes, maybe we can stay online to finish and talk about a couple of follow-up steps I need to process. But really appreciate your time and thanks so much.
Okay, thank you. Thank you very much.
Thank you.